All right, so this week, the two options are to do a payroll program or calculate pi. So it's quite a range of possibilities. I would encourage those physics students to do the pi, and those who don't have an affinity for science, then you can do the payroll version. I don't have a whole lot to say about the payroll version, except be sure you test everything and work through a couple of those options carefully to be sure that they compute the payroll accurately. So there's 4 options. I would also like the payroll program to iterate so that I can calculate multiple payrolls of different types in the same run. So it's not just a straight through program, it should iterate. All right? So that's really all I want to say about the payroll program. Please iterate. Let me calculate multiple payrolls. Okay, so for pi, right, and I do have that in the payroll. Allow the program to repeatedly calculate the payroll for an unknown number of employees. Have a special payroll type code to stop the program. So for pi, again, do not preset the answer. You don't know that pi is 3.1415926. You don't know that. You're going to calculate that using the Taylor series equation that the book does give you, right? Pi is 4 minus 4/3 plus 4/5 minus 4/7 plus 4/9 minus 4/11, and so on. What I'm interested in you entering is how many significant digits do we want? Pi can never be exactly calculated, right? I don't know how far we are, how many billions of digits we have pi to, but it's sort of an ongoing thing. So we're going to kind of see the mathematical process that's involved with this. So we're going to stop the program, not when we exactly have pi, but when we have close enough to what we're after, pi. And it's the numerical process that I'm after you to understand. That calculating an approximation with an iterative process like this has to reach a threshold to stop. Okay? So each iteration adds to the accuracy. That's the idea. As we add one more term of pi, we add a little bit to the accuracy of pi. If you look at the trend of the terms, like it's 4/3, 4/5, 4/7, 4/9, 4/11, 4/999, 4/1001. The trend is that each term added and subtracted in and out is smaller and smaller and smaller. And so you have to know when you want to stop. And so what we're going to do is, what I want you to do is put in a significant number of digits, 3, 5, 6, 7, and we can stop at that. Please do this in double precision so that use doubles, not floats. So that you can go further. But the more significant digits you go, the number of iterations significantly go up. And so it's not linear, by the way. All right. The book suggests printing all the terms out. Don't do that. Print the first few terms, and then I would like you to count how many terms it took to reach the accuracy threshold you set. So print a few terms at the beginning, but don't print all of the terms. I don't want to see 20,000 approximations of pi. Right? Just print the first few for 10 and stop. All right, just to show that you've got your program working. All right, so print the first 10 terms, stop, and then stop printing, but do count the number of iterations. because it'll be interesting. You'll see the pattern. How many iterations it takes for 3, how many iterations it takes for 4 significant digits, how many iterations it takes for 5. You will see a very clear pattern emerging. All right, so you do that. So you put in the number of digits, and what we want to do is on each iteration of pi, it gets closer and closer. The difference of the approximation shrinks as we get more and more accurate. So we decide on how accurate we want it based on the number of significant digits. In other words, when we say that we want 3 significant digits, we want to get an approximation in which the 3.14 doesn't change. That in the hundredths digit, it doesn't change anymore. When I say it's 5 digits, then the 10,000th digit is not changing anymore. The 100,000th digit may still be going up and down and doing things. And other more least significant digits are continuing to change. But we're going to kind of cut it off, right, and see if there's a change. And a way to do that is to calculate a delta. So when we say that we want 3 significant digits, then basically we are taking the number of digits, raise it to 10, raise 10 to that, I'm sorry, and divide that by 1. In other words, get the reciprocal. And that is a threshold that we want. So so you input n digits. All right. Calculate delta as 1 divided by 10 to the n digits. All right. So that 3 significant digits becomes a delta of 1 thousandths. All right. So that when a successive pi calculation is less than 1/1000th, if the difference between 2 successive pi calculations is less than 1/1000th, we can stop. That's the idea. That's what happens when you do approximations and calculate. You do a calculation as the previous value, do a new calculation, take the difference, and if that difference is less than the delta, we're there. Right? Because mathematically we're converging. Future calculations are going to get smaller and smaller and smaller. That's the idea. Right? So calculate a delta, and then your algorithm is, old pi is, what's it start out? The formula says pi is 4 minus 4/3 plus 4/5, or basically extending that, pi equals 4/1 minus 4/3 plus 4/5. Okay. So we see alternating signs in the sequence. The numerator is always 4. The denominator is increasing by 2. It's 1, 3, right? So we say old pi is 4. The denominator can start out as 3. All right. We could say new pi. Let me change that. I'll say old pi is 0. New pi is 4. Change my mind. I didn't sketch this out. I probably should have sketched it out right ahead of time. And then I say while old pi, this is the threshold check, while the absolute value of old pi minus new pi is greater than delta, greater than or equal, equality of doubles is usually never happen. Exact equal doubles never happen. You almost always want to compare delta, or you always want to compare doubles to some epsilon or delta, some threshold. So while the difference between the last calculation and the current calculation is still greater than delta, we keep going. That's the idea. Nu pi equals old pi plus 4 divided by the denominator. Actually, to get this really going cool, I'm practically going to give you the algorithm here. That's why it's worth coming. All right. The first term is 4. I already have 4 over 1. The second term is going to be 4 over minus 3. That's the subtraction. You don't have to come up with an if statement to say, well, I'm on the even term, on the odd term, and then I can add or subtract. Oh, no. I can, I can, let's see, do I want to do that? No, I don't want to do that. You got it. All right. I'll add another one. Let's do this. Sine equals minus 1. All right. So it's 4 over denom times sine. All right. So that gives me my 4/3 as my nu pi. Then what I can do is set up, right, the denominator. What's the next denominator going to be? How do the denominators go? They go 1, 3, 5, 7, 9, right? So the next denominator is what? Right? Plus equals 2. Right? What's the next sign going to be?
Negative.
What's that?
Negative.
Yeah, it's going to switch, right? So I want to go from minus 1 to 1. Okay. Everyone likes to multiply by minus 1. All you have to do is switch the sign. There you go. Print nu pi. You can retrofit that to print the first 10 terms. You can retrofit that to count up the number of iterations. So it's not complicated. It's not a big algorithm. But the gist of it is you input the number of digits, calculate a delta based on that, okay, which is the power of 10 raised to the number of digits and the reciprocal of that. That's your delta. And then I've transformed the Taylor series into a nice little iteration. We don't know how far we'll go, so we'll count. I've had students somehow figure out the formula and then set up for loops. That's again sort of pre-calculated, sort of like knowing what pi is. I don't want you to know that. Questions? Make sense? You can fix that up. You will be a little bit challenged. You will have to search out the absolute value. Make sure you get the right one, the right absolute value. Right? There are multiple versions of the absolute value function, so be sure you get the right one for floating point numbers, for doubles. So is that simpler than what you thought you'd see? Okay. Next week is on the Towers of Hanoi, a recursion problem, and then a high-low guessing game. Would you like me to talk about them? Let me just go ahead. Right? Unless you have questions, I'll go ahead and talk about primarily the high-low guessing game. The Towers of Hanoi problem is fairly straightforward. You can see I have a very little augmented description to that. So what is in the book is what I want you to implement. Okay. Are you know, if you're not familiar with the Towers of Hanoi problem, you're welcome to take a look at it so you can figure it out, or just go to the guessing game high-low, right? I'm thinking of a number between 1 and 1,000, and I make a guess, and the obvious first guess should be what? 500, right? Then I say high, it's higher or lower, and I say lower, so you go to 250, and then you say lower and you go to 125, and you say higher, and then you've got to do the math, right? To do whatever it is middle between 125 and 250, right? So you have to mentally, in the game, keep track of two numbers and basically get the middle of the two. And if you're guessing a number between 1 and 1,000, you should always be able to narrow down in 10 guesses. Because if you cut your problem set in half, which is exactly what you're doing, you're cutting it in half on each guess, you can only cut in half 1,000 10 times until you're down to 1 or less. Log base 2 of 1,000 is 10, less than 10. It's cool. The guessing game, you do that operation. I mean, we can do this with 1,000,000. I'm going to guess a number between 1 and 1,000,000. I can do it 20 times, 20 guesses or less. It's doable. Now the mental math is a little bit tougher. Taking the average of two numbers that's 6 digits long is not. It's humanly possible, but it's probably fairly error-prone for most of us. In this game, in this project, it's fairly straightforward to set up. When you should stop the iteration. I just want to say a couple things here. When you stop the iteration, you should do it when the guess is done. I've had students stop the program after 10 iterations and say, sorry, but if it's going to take me 12 iterations, let me do the 12. Because sometimes you have a mental lapse and you don't do the average correct, or you didn't go higher, you went lower and you realized that you went the wrong way and you still have to keep guessing. So don't stop until the user guesses. Then you exit the loop. Then you can count how many guesses there were. Then you can chide the person, you should have done it in 10 or less. Or, very good, you know the secret and you got it in 10, or you're very good and you did it less than 10. And that's my goal, is to always do it in 8 or 9. Okay. Usually, about half the time I have to go to 10, but there are ways to sometimes maybe hit the answer a little faster than 10. It's sometimes doable. Not always doable in 9, but it's a game. It keeps me entertained when I look at 12 of these projects. I've got to play the game to see if it works. The other thing is the random number generator. Okay, so in the book, they will be describing a random number generator. You only need to create one random number generator. And if I run the program, if you ask if I want to run the program again, you don't have to create another random number generator, just ask for another random number. Random number generators are meant to create a sequence of random numbers, so go with that. You also want to seed the random number generator with time 0. Okay. So please do that. Right? Be sure you do seed the random number generator with a call to the time function as shown in the text. So it is buried in the reading, so be sure you use that correctly. That's often a reason for a resubmit, is that I will see a bad use of the random number generator. So be sure that you check that out carefully. Again, the reporting of chiding or congratulations or the secret kind of message, that should not be buried inside the loop. I've seen that done. It's just odd to me that that would be inside the iterative guessing loop. Oh, you found the guess. Exit the loop when the guess is correct. Then you can say, based on the count, what you should do. But be sure that that's outside the loop. That's just good design. The loop should do what just the loop is meant for, and that's the guessing. Right? You should not bury other things inside the loop that is really just the last time through. If it's the last time through, then do it outside the loop. Okay? I will I can review that next week. And then we will get into the maze problem. Okay? So it'll be a matrix set up, and you'll solve a matrix. Solve a maze within the matrix. And so it becomes a little more substantial of a program. It's not hard. It gets tedious because how many directions are there in a maze? 4. How many? So you are heading in a particular direction, but you have 4 choices. Go left, right, forward, or backwards. And so those 16 combinations get tedious. And you actually have to do some tedious programming. So I'll start getting into that a little bit next week. All right, otherwise, that's it. That's a review for today. And if you run into any problems, questions, let me know.